organizer. I can see the one organizer here for putting together such a wonderful conference. It's like so nice place, and just talking to you is so blissful for me. I'm sort of an outsider. Came from a different field. Started working on this CFT for like the last 3-4 years. But it's really great to kind of learn a lot of things from you for the whole week. So I'm going to talk about this relatively recent work with Harini, but it would be based on the main ingredients came from this my work with Jin, Guillaume, and E. So I'll mention like whatever the kind of ingredients came from that work and what is new results that we got in collaboration with Harini and Andre. So I think throughout this week we have seen different kind of notion of this conformal blocks. I'll try to review some of these notions, and the main sort of the goal would be to kind of understand this semi-classical limit, or kind of like derive some methodology through which we can study the semi-classical limit of Virasoro conformal block. And so there is a nice kind of relation for conformal blocks, semi-classical conformal blocks proposed in the literature of gauge theory, and through the AGT it should be also valid for semi-classical limit of conformal blocks. That's this Nekrasov-Grossly-Shatajvili relation. So I'll kind of talk about that and how to prove this in the context of this Liouville conformal block or semi-classical limit. Then a little bit of this connection problem. I'll mention what exactly I meant by this. And depending on time, we'll kind of touch upon some of the proof ideas for the main results of this project. Okay, so this is more or less the plan. So I'll start, and then for this whole talk, I'll focus on one point towards conformal block, and this is sort of complicated enough for me or for us to understand, and the hope is that if you understand this well, all these kind of properties, like it should not be that hard to kind of replicate it in for other conformal blocks, like for blocks for sphere, 4-point sphere, or for more points, higher genus, and so on and so forth. So this is the maybe again the same problem. Maybe if
you go into some full screen mode, maybe.
Yeah. So let's start with this first principle definition of conformal blocks, which I think came in the work of BPZ perhaps first, and like later Jomolodchikov also had like a different sort of a reformulation of this definition. I'll mention that as well. But this sort of like comes through this this Virasoro generator, and like this and the definition of this primary field, which is determined through this constraints, like constraints how it acts on the Virasoro generators. I'll take some sort of like a trace for this primary operators multiplied with this q power 2L naught. And this formal power series, this is exactly what Golan and Remy, they recovered in their paper, Second paper. And before their work, it was not clear whether this is this formal power series is convergent. And what they showed is that this is basically absolutely convergent power series for almost all values of P. P is supposedly this internal momentum parameter. But this formal power series has like a lot of structures, and this is perhaps like what when we study conformal blocks, I think like what I heard on the physics side, that like this structures has been like this became or turns out to be very useful in the sense to compute the full conformal blocks. And the structure that I'm referring to is this this topological recursion, which comes through this kind of some observation that how this residue of this conformal block behaves as a function of this internal momentum parameter P. So what it turns out that like what Topological noticed that like if this torus conformal block, and this is also true for the spherical conformal block as well, as a function of P, it has like simple poles at a very specific places. It's like at CAG zeros. And the residue at this simple poles are very nicely behaved in the sense that like residue at like this PMN, which is one of this simple poles, is given by this factor RMN, this is the one that you see, times the conformal block at this delta where this P is now kind of flipped, the N become minus N. And this is for this N and M that I'm choosing here are positive, like both are positive, and the same thing is valid for when both of them are negative as well. And this, you sort of like have this similar phenomena. You just have to flip the sign N to minus N. And so this leads to this kind of nice kind of expansion, residue expansion. You still need to prove that, like for which, of course, like in when John Jacob like sort of putting it together, he noticed that this limit of this conformal block as P goes to infinity is also equals to 1. So that sort of leads to this the very nice residue expansion. And if you sort of keep on applying this expansion over and over again on this conformal block, it leads to a very nice recursive relation for the coefficients of this formal power series. And this is called called like a geometrical recursion. But again, of course, like this recursion gives a very nice way to compute all the coefficients. It was not clear whether it is sufficient to prove the convergence of the power series. So this is like another very nice description of the same power series that we've seen, and that's also coincide with what Cohen and Remy and Vincent got. And I also wanted to highlight this other power series, which is kind of like slightly different looking. But again, it's a power series in Q, and it comes from this connection to this supersymmetric gauge theory, and it's basically exactly equals to this Nekrasov instant partition function. And the same power series that we have seen in earlier up to some like constant factor could be written like in this following way, where the coefficients are now have some description in terms of this some summation over 2 Young tableau. Again, like from the this Virasoro side, there is a similar representation, but it turns out they are not the same kind of like representation of the coefficients. And it was not clear for some time that why this should match, but in the work of Liouville in 2010, what they showed is that this expansion, the coefficients also satisfy the geometrical recursion, which proves that these two kind of like power series are basically same. But it was still not clear up to that point that why this power series should be convergent, or what are the kind of analytical properties of the power series. Okay, so what is the goal of this talk is to understand, to meaningfully understand how we can make sense of this power series, maybe study some analytical properties of this power series. And in particular, can we take this semi-classical limit, by which I mean that like we take this logarithm of this summation formula that I was kind of flashing, and then we multiply it with this b squared. B is this related to this gamma that you are seeing in this CFT in the course of Guillaume and Remy. We'll try to sort of take this limit and see how can we say something about this limit. And also, like the Colin and Guillaume, they mentioned that this conformal blocks has this representation as like this. There's a flat connection, projective flat connection over the principal bundle in the quantized Teichmüller space. So that kind of interpretation. So what is the implication of that interpretation? As you take the semiclassical limit, this is what exactly prescribed by this Nekrasov-Rossli-Shatasvili connection relation. I will see like how we can recover that in the context of torus one-point conformal block. And so I'll mention about this connection formula for spherical, the semiclassical limit of the spherical BPZ, which is the Hein equation, and why we are kind of interested from the perspective of one-point torus. That's kind of the main motivation I wanted to kind of convey. So this is a kind of the goal of the talk. Any questions so far? Okay, so if not, so what I want to kind of like change the gear to is that I showed you all this kind of nice kind of formal properties like description of conformal blocks, 3 different kinds possibly. And these are all coming from either algebra or gauge theory and to some extent also probability now through because of the work of Coulomb, Remy, and others. But then for studying the semiclassical limit or other analytical properties, what I'm going to do is that I'm going to propose an entirely different definition of conformal block. And what it turns out to be the case is that that is much more sort of amenable for studying these analytical properties for this conformal block. And that would be also done through like some probabilistic objects. And what I'm going to do is that like now introduce those probabilistic objects. Okay, so what I need, very minimal thing. I need a, like as in Remy and Guillaume's talk, they were using Gaussian free field. I need a much more simpler version of it, a log correlated field on the interval 0, 1. And I'll start with a very kind of like the primitive version of this log correlated field, which has this following the correlation structure. And it has, of course, like infinite variance. It lives in the space of distribution. And on the top of it, it has like a nice representation as well as a sum of like Gaussian independent random variables. And for constructing this conformal block, I'll need a little more kind of like sophistication on the top of this simple field that I introduced. But this new thing that I'm going to add on the top of this log correlated field will be a smooth field. So what I would do is that I will add a smooth Gaussian field on the top of Y, and that will still make that will keep the correlation structure still log correlated, but it would be of slightly different form. Instead of like this exponential log of difference up to exponential, now you have a log of theta function. And as you can see, theta function, this is kind of like what gets us closer to the forming some field over the torus. Okay, so this is what I need, like this y tau field. And I'm going to propose a really different structure of conformal block. And this is kind of like what our proposal is. And it's just very simple looking. So we will just need an expectation of some integral, some power of some integral of this log correlated field, where this alpha is this weight of this marked point, p is this internal momentum parameter, and this normalization z, which has like very explicit form. Like if I get time later, I'll show you this kind of how it looks like. It's like some ratio of double gamma function. But the core fact is that we chose it in a way that like this conformal block would have this limiting behavior, such that this as q goes to 0, this would have limit 1, and as p goes to infinity, this would have limit 1 as well.
Sorry, so is there some reason why alpha appears twice? So you have alpha b and then you have also alpha over b? And then
So this is
p appears only once?
Yeah, so this is the range where this probabilistic definition we can make sense of, beyond which like this probabilistic definition does not hold.
No, I'm not asking about the range, I'm asking about the formula. In the formula you have two alpha appears in two different places, right?
Right, so alpha is here, and alpha is here, yes.
And p is only at one place.
Yes.
So is there a simple reason?
There is no simple reason.
So here it's important that Q is real, right? It will not be true.
So we can make sense of Q complex by applying the Gersonov. So if you apply the Gersonov, you can like take out this independent part outside. So then it would be like an analytic function of Q.
But then how do you guess this formula?
That's it.
Can you show the theta again? Sorry, can you show the theta again?
Can I make a very quick comment? I just wanted to say that P is going to be the eternal momentum in the sense that on the torus, alpha is actually the monodromy around the singularity, and P is the monodromy around the triangle, which is going to be here. And the conformal block is normalized in a very specific way to have monodromy that behaves in a, it's a normalization essentially. And through this normalization, you can see that P should have that form and alpha should appear the way it appears. Well, that's in retrospect. How they guessed it, I don't know.
So there is, so this is something, I guess I can tell you a little bit of story. So we were kind of drunk in one night, and like we were checking like what kind of like this Gaussian field type of formula can work for this series, and we were lucky enough to get a formula like this. But now through this work with Shin and others, we have a more kind of systematic procedure to get a GMC expression of a conformal block through this boundary bootstrap. Basically, what you do is that you take this boundary bootstrap, and it turns out to be the case that it's a Fourier transform of like a conformal block, and then you do the inverse Fourier transform to get a or GMC type formula for the conformal block. So that's sort of more kind of systematic way. But then this one, and it turns out like they're actually not like, it does not look like, if you do this procedure, it does not look like the same, but it turns out that they are kind of share the same series.
Just one further question. That works because it's a special conformal block. If you take 10 points on the sphere, say, can you invert the Fourier transform? Because it's not that simple, right?
It's not that simple for, I think, for 5 or 6 points we can do it, or 10 points.
You still can get further than 4 points.
I think we can do further.
Yeah, 4 probably, but more you have an example where it works?
If you
Like 5, you know how to do it.
yeah, I think so. Yeah, I guess like as you increase the more points, but at the end you just still get this inverse Fourier transform type formula, and if you want to do like extract some analytical properties, maybe study the semiclassical limit, that still sort of like would be enough to kind of crank the analysis through. Okay, so what turns out to be the case, and this is sort of like came out in our work, the previous work with Shin, Guillaume, and E, almost like 3 years ago, or actually more, that this 3 different power series that I showed you, and the probabilistic conformal block that I was there in the previous slide. They are so first of all, this power series, we were able to show that they are convergent in this previous work. When Q is in a ball with a radius which is greater than 1/2, but maybe not exactly 1, but with the new work we would be able to show it. This radius of convergence would be exactly equals to 1. And what is more kind of intriguing is that all this power series would coincide with this probabilistic formula that was there in the previous slide. So this probabilistic expression, if you kind of expand it as a power series in Q, we'll get this. The coefficient would satisfy this topological recursion. Okay, so then, this kind of like, and one few nice thing that I wanted to say about this is that the dependence of this formula on P is very nice in the sense that you can sort of in this work, previous work, we were able to show that this, of course, this would be finite, this formula makes sense for any real value of P. But not only that, you can extend the formula on a kind of small band around the real line as well. So that sort of gives the opportunity to extend the idea of this convergence of the power series beyond the real line. And the constraint that was there in this Golan and Remy and others' work, that it has to be absolute convergence for almost all value of P, that is not there at least for this formula. So because of this kind of nice structure, or of this analytic property, one can hope to sort of study this goal that we set, that this taking the semi-classical limit, and that's exactly what we did in this work with Harini and Andre. So when we started looking at the semi-classical limit, we were not familiar with this conjecture of topological, especially sort of formulated for 4-point sphere, but we take this liberty to also kind of formulate it for the torus and try to see sort of with the right analog. So this is the kind of analog of geometrical conjecture for the torus. So the first kind of proposal is that the limit of this the conformal block, this log of this conformal block times this b square as b goes to 0 should exist, and that's the first proposal, and it's called exponentiation. And the second one is that this the semi-classical limit, this tau derivative of the semi-classical limit. By the way, this q is e power I pi tau. That's how this tau dependence is coming into this semi-classical limit. And so this would be the accessory parameter for the Lamé equation. So that's sort of the other proposal. And what the kind of more nice thing that we are able to show is that this Lamé equation, at least in this, there is a kind of special solution for the structure of the Lamé equation. And we have an explicit form of this special solution. Now what it gives us is that if you plug in this form here, you get an explicit form of the semi-classical conformal block in terms of this theta function, which I think was not kind of I haven't seen anywhere in the physics literature as well. Explicitly, I guess there is some expression of the semi-classical limit as a power series, which is this Nekrasov-Shatashvili expression, but as just explicit some combinations of the theta function was not something that we were able to find, but maybe some of the physicists in the room probably have known it before. Okay, so then now the question is can we say more? So the next thing that where I'm heading to is that this like what does this the semi-classical limit like? What is the kind of geometric implication of the semi-classical limit? So, like this, I mentioned that the Tishner and others has this kind of view of like looking at this conformal block as a this flat connection over the principal bundle in the quantized bipolar space. Now, when you take the semi-classical limit, what is the sort of implication of that? And so that is sort of like captured by this Nekrasov-Roslin-Shadashvili relation, and that is where I'm heading to next. And for this, what I just need is that this kind of the idea of this trace coordinates on this one punctured torus. So I think this is something like which probably appeared a few times during this conference, but I don't have to kind of like mention too much things. So we'll take this this fundamental group on the one punctured torus and the representation, and take the trace and it has like very kind of fixed like the known Casimir, and then like if you kind of like take this fix this Casimir, that would give a symplectic leaf on this space of modular space, and the Goldman brackets gives us a Poisson manifold structure. And what we need is that like actually like transforming the space coordinate to this length twist coordinate, which would give us this basically the Darboux coordinates, and this has a kind of explicit relation. And we'll see like why I'm kind of introducing this in a second. So basically, this transformation are formulated in a way that like this new coordinates kind of satisfy this particular Goldman bracket structure, and that would be sort of showing up in the Nekrasov-Roslin-Shadashvili relation. Now this there is for two different curves. So on the torus, you get two different coordinates, and they are kind of like there's a consistency relation. Like one of like if you know two of them, you can kind of determine the other two by this two relation, where this n is basically this this arc cost of this trace of this Casimir element.
I have a question.
Yeah.
How to obtain this kind of relation?
How to know? How to find?
Yeah.
So basically, what happens is that like you have this length twist coordinate for around A and around B, and you write this like the rho A and rho B in terms of LA and LB, LA and tau A. Similarly, you can write the rho B, rho A and rho B, or trace of rho A and rho B as a function of LA and LB and tau B. So that like, and then you equate them, and this gives basically you get the two equations, and you get like this. After some simplification, you get this two relation that I wrote down here.
So this only known for one puncture torus, or is known for a very large class?
So for a larger class, I guess like if you take this, I think if you take this, let's say higher genus or multiple points, you get like at least 2g minus 2 plus n many coordinates. And if you have more, then they would have like some consistency relation among them as well. Yeah, for the sphere also, you get like one set of coordinates.
But can you express any pair in terms of other two pairs?
No, not it's only this relation is kind of true for one puncture torus.
Yes.
For if you take like higher genus, you definitely should get like there are like two, I forgot what is the exact number. It was probably 2g minus 2 plus n many independent coordinates. And if you have more than like more other length twist pair, you should be able to determine those as a function of this independent set of independent.
But I mean here, can you express LB, L tau B in terms of LA tau A?
I think you need LA up to some periodicity. Yes. So this Nekrasov-Rosalie inverse correspondence basically was proposed or conjectured in the context of, again, the sketch theory. So, like I think for the Nekrasov partition function should satisfy this relation, and through AGT that should be also valid for the conformal blocks. So the first sort of proposal for this correspondence is basically same as this this Geometry-Chekhov conjecture, the second part of the Geometry-Chekhov conjecture, which is this if you take this tau derivative of the semi-classical limit, that should be the accessory parameter of the Lemma equation. So it's the same. And then if you take this force here, 4 point, this analog would be the t derivative of the semi-classical limit should be the accessory parameter of the Hein equation. So that part remains same. The second part is that like this this p naught, which is this internal momentum parameter, and this p naught derivative of the semi-classical limit, that would produce the length twist coordinate on this one function torus. So this gives a symplectic structure, produces a symplectic structure on this one function torus, and then that's sort of the crux of the proposal. And we were so the main sort of like the kind of thing to show here is that this tau a part is basically equals to this p naught derivative of the semi-classical limit. Now I talked about the implication that what is the meaning of tau derivative of phi, which is basically the accessory parameter of the Lemma equation, and p naught derivative of phi, which turns out to be this twist coordinate for the semi-classical limit, and it is still a function of this alpha naught. Now the question is, if you take the derivative with respect to alpha naught, does it have any implication? So what I'm going to show next is that it also has some physical meaning, and that sort of like leads us to this connection problem, or looking towards this connection problem. So
may I ask? So this LA to A, they are related, right? In the according to your formula. So which means
LA tau A are kind of independent. LA tau A and LB tau B are kind of.
no. In the last formula, so they are related because they are functions of. Can you show this next?
Oh, right. Mm-hmm.
So alpha 0, p0. Okay, p0 is LA, and Q is a parameter. So this formula suggests that they are related.
Yes. So basically, what is going on here is that the phi is acting as a generating function.
Yeah. So since they are related, so this defines a Lagrangian.
Yes. Yeah. Exactly.
What is the geometric meaning of this Lagrangian?
What is the geometric meaning? Like.
I mean, why it is distinguished? There are infinitely many Lagrangians, but somehow this is something special which comes out from your conformal block.
I guess like probably don't fully understand the right implication of your question. Maybe.
Okay.
And if I try to say that it is a Malebranche divisor, the manifold where some tau function vanishes, will it give some answer or not?
Okay, so what I was kind of like planning to say is that this this derivative with respect to alpha naught also has a kind of a physical meaning in the sense that, or some meaning, in the sense that it turns out that if you take this special solution and take this, send this z to 0, the boundary limit is actually given by this, like the alpha naught derivative of like this, the semiclassical limit. And sort of like for in this integrable ODEs, like the when we take this boundary limit, like the natural question to kind of ask for is that is there some sort of this connection formula, which probably more well formulated in the case of this spherical BPZ. We haven't kind of seen any something similar to this for the Lemay equation in the literature, but this is something like what motivates us to kind of like look for similar result for integrable ODE. And this is something like which kind of intrigues us that like in the literature something like this exists. So for this is like the spherical BPZ. Basically, if you take the semiclassical limit of the BPZ, 5-point sphere correlation with one degenerate insertion. And where E is the accessory parameter, this should be the semiclassical limit of the 4-point sphere, exactly in the same way as the case of this Lemay equation. And so for this Hoyne equation, it is kind of like people are interested in knowing this kind of limiting behavior of the solution, canonical solution, as this z goes to 0 and z goes to 1. And looking at this kind of like the object, which is basically like the ratios of, or ratios in the metric sense of this sort of monodromy matrix when you get around 0 and around 1. And this is sort of like the what sort of intrigues us to kind of like look for similar result for torus. And then that's the reason why we sort of looked at this boundary result that I showed you, that basically this connection matrix has a very explicit form in the sense that it would be some this matrix times a scalar, where each of the element of this matrix that I wrote here are basically ratios of explicit gamma function, but it is multiplied by this derivative of this semiclassical limit at this kind of the parameters. And the one that I showed you for the torus conformal block has a similar vibe in the sense that like the when you look at the solution at the boundary, we are also seeing some sort of like this derivative of the semiclassical limit at this at this parameters of the vertex operator. Now, so this is something of work in progress. Probably like I should not say much about this. That like we were kind of like trying to prove this result for the Hoyne, starting from like a very first principle idea, in the sense that we looked at this instead of like taking this CFT route, thinking G as a semiclassical limit, we define G through like this this primitive of this one closed one form, and which is kind of slight modification of this Jimbo Miwa Uno one form, and then proving that this the connection constant for the Hoyne would be exactly of the same form, same structure. So G, if this if the CFT route is taken, then this G would be should be essentially the semiclassical limit of the spherical 4-point correlation conformal. So
is it related to Drinfeld associated, this object C?
To what?
Drinfeld associated in quasi-Hopf algebra theory.
I don't know much about that. Probably. I guess like the OLED differential.
Because he defined his associated by using approaching z to 0 and 1 and some ratio of something, I don't remember, but a very similar formula.
So I guess like I have some time to say a little bit of the proof idea. So then let me just like say the summary of the strategy. So we're going to make use of this BPZ question for and then our object is constructed of Gaussian multiplicative queues, and we want sort of this b goes to 0 limit. And for this, we need to derive some sort of estimate, and we needed some kind of like quote unquote dealing with some b derivative of the Gaussian multiplicative queues measure. So the tightness of this sequence in the semi-classical limit would come from some combination of this estimates coming from BPZ and this derivative GMC. And this would give us a subsequential limit for this light insertion to this Lemay equation. And for the heavy insertion, we get a limit towards this Hamilton-Jacobi. Now, for the uniqueness, we use some uniqueness theory for the Lemay equation, and that gives us the expression of the semi-classical limit that I showed you, like in terms of this combination of the theta functions. Okay, so then I guess like we have seen BPZ equation several times, but what makes it special in this situation is that we have also a probabilistic way of deforming or putting a degenerate insertion in our conformal block, and showing that would satisfy the BPZ equation. So if you remember the probabilistic expression that I showed you was without this rate theta function factor, and without this is what we call as undeformed conformal block. This is what satisfies this or coincides with this geometrical recursion formal series. But then when we insert this extra theta function, it's one way to kind of deform this probabilistic expression. And it turns out that after doing this deformation, it satisfies this non-stationary Lemay equation, which is basically the BPZ equation for this two-point torus with one degenerate insertion. This non-stationary Lemay actually was studied in different contexts. It's sort of like also a very popular PD to study, and then it appeared in also vertex model. I came from this kind of community of vertex model, and kind of intriguing to see the same PD kind of appearing. And it's related to this quantum Penn-Lavey equation. So I guess also some sort of this OP type of behavior satisfied by this deformation, which kind of shows that it's probably the right way to deform the conformal block. So as U goes to 0, the deformation goes to 0, it splits into this kind of linear combination of these two undeformed conformal block with the kind of the shift in this alpha parameter. Okay, so this is what I was kind of trying to tell you when, I mentioned this light and heavy insertion. Basically, light insertion, as all of us probably know, that it corresponds to the deforming with this exponent chi equals to b, which the chi will show up here and some factor here as well. And the heavy insertion corresponds to the case when chi equals to 1 over b. What it turns out to be the case is that if you take chi to b equals to b, there is kind of very nice sort of decoupling happens. This deformed conformal block splits into two factors. So the first part would be the one where we get this undeformed conformal block, the one without any u factor. And the second part would have this exponential of some function dependent on u, but then it does not have the kind of this very wild power of 1 over b squared. So this is something what we showed, like using this this derivative GNC, that the splitting is kind of true, and we have to also kind of control this error between these two terms, and like the error controlling part coming from this, a lot of technical estimates. But then once we have this, if you plug that in, you get a relation directly that this the limit, the semi-classical limit of this undeformed part would be the accessory parameter of the Lemon equation, and this part kind of like solves the would be the solution of this the corresponding Lemon equation. So since we have an explicit form of this, that gives us this gamma tilde that I was showing you, and at the end, this gamma, this part leads to explicit kind of formula for the semi-classical limit. So that's a kind of the whole ballgame. On the other hand, if you take this chi equals to this 2 over gamma basically is 1 over b, then I think I should be replacing this with typo. Then we get the limit, this limit of this BPZ basically would be this Hamilton-Jacobi equation, and this would be like, you can think of it as a Lagrangian for this two-particle non-autonomous Calogero over integrable system. So this is sort of like the idea of this semi-classical limit part, or the kind of what goes inside this, proving this geomological conjecture. And then the second part of this inner S, which basically showing this this fact that the P naught derivative of the semi-classical limit is the twist parameter of this and this one puncture torus, twist coordinate. So that actually comes from like this this modular relation, which what Jean was talking about, that the conformal block at the Q is related to the conformal block at Q tilde through the 6J symbol Poisson-Teichner formula for a torus, 1-point torus, where this modular kernel has this very explicit expression. This is this this I part is this like the 6J symbol. This is the this extra part is basically this coming from this BPZ equation. It's like again some ratios of double gamma function. And so what it turns out to be the case is that, like, to show this fact that this this P naught derivative of the twist parameter, that as we take this b goes to 0 limit, this I has a integral, like or m has an integral, which is this I part. The saddle point equation for this would give us this, the first consistency relation. Again, like, it needs some sort of technical estimates to show that y sort of like this, the integral would concentrate around this saddle point for this integral, but then it's just like the same equation that we showed you before. On the other hand, like this modular relation itself has a kind of integral outside. And that you have to take also a saddle point for that integral. So that would lead to the second consistency relation that I showed you. And so this is basically like this two together would determine. So if you fix, if you have this, so LA corresponds to the A cycle monodromy, which is this P naught. LB corresponds to the B cycle monodromy, which is basically this P naught prime, basically, which is the basically A cycle monodromy of the conformal block corresponding to the Q tilde parameter. And this LA and LB would determine through this, like the tau A and tau B, and it turns out this the right choice for tau A and tau B. And this equation is this the derivative of the conformal block with respect to P naught and P naught high.
Is there some misprint? So there are two pairs of LA tau A.
Oh, right, yes, this would be the Okay, so stop it 5 minutes ago. I guess like to summarize, like I showed you this kind of probabilistic expression for one-point torus. One can take the semiclassical limit and prove this NRS relations, and so it also can flash this connection problem for the Hein. Now one can sort of like with this kind of probabilistic expression for the one-point torus and also the four-point sphere case in our paper with Shin and Baojun and others. One can take also the higher order expansion for the conformal blocks, and what the kind of there should be an expression of this higher order terms in terms of like again like some spatial functions, something that I kind of was showing you. So I suppose there could be some, like if one sort of find those out, one can sort of maybe use it for proving or some estimates for topological recursion perhaps. This semiclassical limit for the conformal block for endpoint sphere and other surfaces is also important question. At this point we probably can do endpoint sphere, but then for other surfaces it's not clear. And like I think like during this conference, I started learning more about this confluence, which basically what I understood is that like kind of taking these two singular points, merging with each other, and probably like one idea would be to sort of like take this probabilistic expression, merge this singular points, and then take this semiclassical limit to find this accessory parameter for this confluent Hein or confluent Lamé. And then study the associated connection problem so that we do nice future durations. Okay, so I'll probably stop it here, and thank you very much.
Thank you very much. So we have the time for a few questions.
So for punctured sphere, can you do similar calculation?
Yeah.
And the complexity approximately should be the same.
So one thing I should probably at this point you're a bit behind in terms of how the result looks like for the one-point torus. Is that so we can do the semiclassical to show that this semiclassical limit exists. We're still missing on one point, in that this showing that this would be the accessory parameter for the Hein equation. I think there are some ideas. We're kind of like exploring a few ideas at this point, but it should be also, and there will be similar things as I was showing you. This NRS, like it should also kind of generates this the symplectic structure.
Why you preferred one punctured torus? Why did you prefer one punctured torus over?
The formula looks simpler. So for sphere, the formula is slightly more complicated. So instead of like, so here we have expectation of integral of 1 GMC. For sphere, it would be expectation of product of two such integrals. I guess like in terms of complexity, it's not too much, but like I guess the idea was to kind of nail down the details for the torus first and then go towards the sphere.
So in your semi-classical analysis, do you also need to do some semi-classical analysis for the torus block in order to get this NRS relation? So I think
Yeah, that's right. Yeah.
So you only need to do the first order.
No, we need some estimate for the second order as well. Yes, like the second order. So while looking at it, I realized that you can actually also probably get a explicit form of the second order term.
I see. And this is used in
We'll not be using that, but that's something to explore.
in some bound in the second order.
Yeah. You can write down this as a some. I think that there would be some integral of the field. So my kind of conjecture, probably I should not say like very specifically, but then all the higher order terms should be some sort of like expectation of some Hermite polynomial of integral of Gaussian or this log correlated field. So that should be kind of like able to figure it out.
So the necklace function have very combinatorial expression when you expand that function at some point. And your probabilistic description helps you to obtain such a formula?
Yes, so it coincides exactly with the sort of partition function that we showed.
So can you see some pair of Young diagram? The expression in terms of such a pair of Young diagram?
Yeah, so
Is it naturally appear?
So the way we proved it, like in the paper, it was kind of very roundabout way, and then we don't see exactly this coefficients being like this, expressed in terms of this pair of Young tableau. But if you like take this fact that this two-side match, what it means is that this expression given in terms of pair of two Young tableau is basically some Gaussian integral of some Gaussian multiplicative chaos measure. So that gives like a series of identities, perhaps like not explored before, but I don't know what may come out of those identities. Okay, so I think we should conclude it again.